I'm Tony, and this is Andrew, and our project is on methane aromatization and benzene, and we represent Group 13. So benzene is traditionally procured from petroleum-based resources. However, these resources, like crude oil, are rapidly depleting, and methane can actually be used as an alternate feed for benzene production, and this can be gotten from natural gas. So this graph is showing the natural gas production in the US, and as you can see, it's actually increasing. So methane direct aromatization to benzene is done using heterogeneous catalysts, and these have been shown in literature to successfully produce benzene. And the catalyst is just composed of a support and a loaded metal, which would be the active site for the reaction. And ZSM5, compared to other supports such as silica and magnesia, alumina, and titanium, it has been shown to be the best support for this kind of reaction, MDA reaction. And also, molybdenum has been shown with the highest selectivity and benzene yield compared to other metals that have been tested on ZSM5.
So next we'll discuss the reaction kinetics and equilibrium. First at the top we have our main reaction, which is methane converting to benzene with some hydrogen production. And as you can see from the heat of the reaction, this is an endothermic reaction, so it requires heat. And for our two undesired reactions, we have the methane and benzene coking is what we call it, and that's when it's converted to solid carbon and hydrogen, basically decomposing. And each of these reactions follows the Langmuir-Henshelwood mechanism, and so in this case, both A and B would be methane, and it would actually require 6 methanes attaching to the active site and then subsequently converting to benzene. So next we'll discuss some chosen conditions for our reactor and some assumptions that we made. So we have a steady state, we modeled a steady state isothermal reactor at 1300 Kelvin, and that's because the desired reaction is very thermodynamically unfavorable below this temperature. We chose an inlet pressure of 500 psi, and this is a lot lower than, this is at the low range of natural gas typical inlet pressures. Our target that we wanted to meet to produce was 5,500 gallons per day of benzene, and this is based on the smallest current benzene production plant, so we said if we could meet that, we could at least be profitable. We set the methane feed at 470 kilomoles per hour, and this is actually a pretty high feed flow rate, but we had to have a high feed flow rate to account for the low conversion, as we'll see after the results. And so we modeled a single tube packed bed reactor with an inner diameter of 1 foot, and the assumptions that we made are that there's no catalyst deactivation, and we modeled the gases as ideal gas.
So material and energy balances were solved for based on the previous conditions, and these resulted in differential equations, and they could be solved using MATLAB. And also the Ergun equation was used for the pressure drop along the bed, and that's also a differential equation that was solved with MATLAB. So this first graph is showing our flow rates as a function of the catalyst weight. And as you can see, the benzene is the red and the methane is the blue, and there's not much benzene production compared to the feed of methane that we have. So this graph is showing the pressure versus the weight of catalyst, and we didn't want a pressure drop of more than 10 ATMs. And our inlet pressure, as you can see, was about 34 ATMs. So we chose right at 10 ATM pressure drop, so it would be about 24 ATM for the coming out, the outlet, and that gave us 150 kilograms of catalyst, as the arrow shows. So the arrow showing again 150 grams of catalyst, or kilograms of catalyst on the benzene versus catalyst weight. So this just shows the benzene production. And as you can see, there is a maximum that's to the left at a lower catalyst weight. However, if we chose this lower amount, it would give us a length to diameter ratio that's less than 3. And that's what we needed as a minimum for packed beds, due to the fact that if you have anything less, the flow profile won't be developed properly.
Okay, so some more detailed results from our calculations. Our benzene production is about 7,700 gallons per day, and that's actually higher than our target, so that's good. Our optimum catalyst mass to use inside the reactor is 149 kilograms. The heat duty required to keep the reactor at 1300 Kelvin constantly is 2900 kilowatts. The length of our reactors is 8.8 feet, so almost 9 feet, so that results in a length over diameter ratio which is much greater than 3, so we should have good developed flow. The pressure drop, as we mentioned, is about 148 psi, which is about 10 atmospheres, and the conversion for the main reaction is about 18%.
So in conclusion, methane aromatization with heterogeneous catalysis is successful to an extent. The scale of production that we calculated can compete with the lowest level facility. However, the issue is that there is a large feed flow rate of methane required to actually achieve the production level we need. And also, one thing we didn't take into account was coking and how we deactivate the catalyst. So the carbon would actually deposit on the active sites and decrease the activity of the catalyst, and we wouldn't have as much conversion as we reported here. And also, the high temperatures that are required would be an extremely energy-intensive process.
So here are our references, and thank you for watching.